Oops, what just? Okay. Hello everyone. Welcome back. Today we're going to continue. Today in the 2 hours that I have for you, I'm going to try to explain the idea of gauge theories. Okay. So gauge theories are really the concept of gauge theories and gauge symmetry, which I'll explain in a second, is really a very fundamental one. It's really the sort of basis by which the standard model of particle physics is created. It seems that for reasons that I'm not sure I completely understand myself fully at the deepest level, but it seems that our most careful microscopic understanding of nature doesn't just involve quantum field theory in a general form, it involves a very special kind of quantum field theory called a gauge theory. Today, we're going to learn what a gauge theory is. Okay, let's get started. So I'm going to start. Oh, and before I start gauge theories, I'll just remind you what we did last time. Last time we learned that there's a useful way to think about quantum systems in that if you want to imagine a transition amplitude going from some state to some other state here, this can be a quantum mechanical transition or a quantum field theoretical transition, then what you do is you can do an integral over all of the paths that connect these 2 points, okay? And you do some sort of an integral over d phi, dq, something like that, of the exponential of the action. And this is a useful way to calculate things in quantum field theory. In the last 5 minutes of the lectures, I use this to recalculate for you the 2-point function of the scalar field, okay? And some other admin is that the homework for this part of the course is posted. There are, I think, 4 problems, of which 2 are optional and 2 are mandatory. In that you should really just give them all a try. Yeah, give them all a try. Okay. In particular, there were many questions about the meaning of finite temperature in statistical mechanics and path integrals. So people who care about that should really do question number 2, which is fun, although it's a bit unrelated to the actual direct content of this course. Okay. All right. So now let's get started. So now gauge theories. So the first thing we have to do is understand the idea of gauge symmetry. Okay. So what is gauge symmetry? Now, we're going to start with the simplest example. And to begin, forget about the idea of gauge symmetry for a second. Let us think about a theory with a normal symmetry, a global U1 symmetry. So imagine a theory with a global U1 symmetry. So, okay. Let me give you an example. So for example, let's study the Dirac fermion. Okay. You have studied this theory a little bit earlier. You'll see that the features of this are not really that special. But here is the Dirac fermion theory. Okay. Am I right that everyone has seen this just a few weeks ago? You know what this theory is, correct? Okay. So now this theory is invariant under a global U1 symmetry. And let me explain to you what I mean by that. What I mean is if you transform the fermion field in the following way. So if you take psi and transform it to psi prime, where psi prime is e to the I lambda times psi. Okay, so what I'm doing is I am multiplying psi by a phase, okay? E to the I lambda is a phase. And similarly, that means that psi bar will then go to psi bar prime, which is e to the minus I lambda times psi bar. Then the theory is invariant under this, okay? And let's just understand why that happens. It's quite easy to see why that happens, right? You have an e to the I lambda here. You have an e to the minus I lambda here. These 2 guys cancel, and the action is invariant, okay? Now, this is called a global symmetry, okay? This is a global symmetry. And it's a global symmetry because the parameter lambda that controls the symmetry is just a constant. In other words, it is independent of space-time. Okay. Now, let me just say one more sort of thing that is so obvious that it doesn't make any sense for me to say it, but I'm saying it because it'll change in a second. Also, two field configurations that are related by the symmetry are both physical. Okay. Let me just explain what I mean. If psi is something that, some field that does something, then psi prime is equal to e to the I lambda times psi. If this is physical, then this is also physical. Okay. Now, this is a strange thing to say because, I mean, everything is physical, right? What do I mean? Why am I saying this? And I'm only saying this because in a second, we'll see that some things are actually not physical, and I'll explain why I'm emphasizing this now. Okay. Okay. So that's a global symmetry. Now, here is an idea, which turns out to be a useful one. Let's do something different. Let's imagine that we have a symmetry like this. Sorry, imagine that we have a theory, excuse me. Imagine that we have a theory that is invariant under a symmetry where the symmetry parameter varies in space-time. Okay. In other words, what I want is, I want that psi of x goes to psi prime of x, which now equals to e to the I lambda of x psi of x. Okay. This is crucial. Lambda, the space-time parameter, the parameter that controls the symmetry, now varies in space-time. So you see, I rotate the field a little bit differently at all different points in space and time. Okay. This idea is called a local symmetry or a gauge symmetry. Okay. This is a gauge symmetry where the symmetry parameter varies in space-time. So you see why it's local because it varies. Okay. This is the idea. Before I go on, are there any questions about this idea? Does this make sense to everyone? We're now going to explore the implications of this for the next 2 hours, but that's the idea. And it turns out to be a very useful one. Is everyone happy with this idea? Any questions? I am seeing no questions. Okay, good. So, all right. Now let's understand what is and is not gauge invariant. So for example, psi of x is not gauge invariant. Okay. Oh, so gauge invariant means invariant under the symmetry. Okay. That it does not change under the symmetry. Excuse me. Excuse me, sorry. Now, so psi of x is not gauge invariant, okay, because it changes like this. Let's try, for example, psi bar of x, psi of x. So this is invariant actually, right? Because how does this thing transform? This goes like psi bar of x, e to the minus I lambda of x, e to the plus I lambda of x, psi bar psi of x. And then these guys cancel. And so psi bar of x, psi of x is invariant. Okay. So in particular, in the Dirac action that we started with, the mass term in the Dirac action is invariant. Okay. Now, notice that we would have had a problem if we evaluated this field at two different points. If it wasn't the same x on these 2 points, there'd be a problem because then it's possible that this lambda of x would not agree with this lambda of x. So because the derivative is comparing the field at two different points, we can imagine it's going to be a problem trying to take a derivative of this field, right? So for example, is partial mu psi of x invariant? Well, no, right? What happens to this guy? We get partial mu e to the I lambda of x psi of x. And now if you work out what this is, well, there's a term, let me just take this e to the I lambda of x out. There's a term where this derivative acts on the lambda, and I get I partial mu lambda, okay? And then there's a term where the partial mu acts on the psi, and we get this, okay? And so not only is this not invariant under the gauge symmetry, it's really kind of ugly. This thing here is causing all kinds of problems, right? It looks really ugly. There's a partial lambda over here, okay? So there is no simple way to get rid of this. And what that means is the Dirac action that I started with, that is action over here, this action is not invariant under a gauge symmetry. Okay. So what is the issue here? The problem really is that we don't know how to take derivatives in the right way of this object. So I'm going to tell you how to fix this, okay? To fix this, we have to invent a new kind of derivative. Called the gauge covariant derivative. Okay. Left an I in here. And now what is this? This is a new thing, which I'm defining for you now. It's a capital D acting on psi. And it's defined to be the normal derivative plus an extra bit here. Okay. I.e. a mu psi. Where this a mu is in principle a new field called the gauge field. That is the meaning of a mu. And E is just a number that I've taken out for convenience. So E is a number. It turns out to be a coupling. Okay. So you remember from a few lectures earlier, A is a field that you studied already. In particular, you studied the Maxwell theory, and A was the Maxwell, the field for the photon. And this is the same A. I'm just sort of introducing it in a slightly more formal way, because later today we're going to generalize beyond that theory to a more general one. Okay. But this is the same A as the one you studied in this section. Okay. Now, so next, what I want to do is I'm going to demand that the gauge covariant derivative transforms nicely. Under gauge transformations. So again, what do I mean by this? Let's examine carefully how this gauge covariant derivative transforms. So if I have this d mu psi, then under a gauge transformation, it becomes something different. It becomes d mu prime psi prime. Okay. And I want to demand, this is my demand here, that this is equal to e to the I lambda of x d mu psi. Okay. So in other words, what I am demanding is that this derivative here transforms with an overall factor of e to the I lambda out front, not in this terrible way with this partial mu lambda floating around. Okay. So this is what I'm going to demand. And now we should see what we need to happen to A to make this happen. Okay. So now I'm going to expand all these sides out. So what is d mu prime psi prime? Well, d mu prime psi prime is equal to, I think I'm going to make my pen a little bit thinner. I'm running out of space here. D mu prime psi prime is equal to partial mu plus i.e. a mu prime times e to the I lambda of x psi of x. Okay. Now let me expand out what this guy is a little bit. If I expand out the derivatives, what do I get? Well, I can take this, I can take the e to the I lambda all the way out here, but I have to make sure I act with the derivative in the right way. And what I find is a term where the derivative acts on the lambda, and there's a term with the a mu floating around, and there's a term where the derivative acts on the psi. Okay, and so I get this thing all together. And now recall that my demand is that this whole thing is just equal to e to the I lambda of x times just d mu acting on psi, which is therefore partial mu plus i.e. a mu acting on psi. Okay. And this part here was the demand. Now we can compare these two lines, and we can see that what we need is, for these two things to be equal, we need a mu prime, in other words, a mu under a gauge transformation is equal to a mu minus 1 over e partial mu lambda. Okay. And psi prime equals to e to the I lambda of x times psi. So let me stress that everything here depends on space and time. So we have psi prime of x equals to this. And similarly, a mu depends on x. Okay. So this is the gauge transformation of A. Okay. If we take A to transform like this under a gauge transformation, then the covariant derivative d mu of psi does transform like this under a gauge transformation. It picks up an overall factor of e to the I lambda of x. Okay. And so now with this, we can write down, so now we know that the following term is gauge invariant. Let me just carefully write this down for you. Let's consider this term, where this is now the gauge covariant derivative. So how does this thing transform? This thing goes to psi bar prime of x times gamma mu d mu prime psi prime of x. And now under a gauge transformation, this is psi bar of x e to the minus I lambda. And this is a gamma mu. And this is e to the plus I lambda times d nu psi of x. And again, these two guys cancel. And so this thing is again gauge invariant. Okay. So we have succeeded in making a gauge invariant Dirac action at the cost of introducing an entirely new field called A. Okay. And so the action, for example, looks like this: psi bar I d slash minus m times psi, where this d slash is gamma mu d mu. In other words, gamma mu partial nu plus i.e. a mu. Sorry. Okay. So we've made a gauge invariant action at the cost of introducing an entirely new field A. Okay. Now, now that we have this field A, we should see what else we can do with it. So to understand what else we can do with A, we should note that d mu psi has a nice gauge transformation property. This is nice. And then so is d nu psi. I can take two derivatives, okay? And so, it makes sense. Let's consider the commutator of two gauge covariant derivatives. Let's consider this commutator. We are quantum physicists. It's good to consider commutators. Let's consider this commutator d nu acting on some field psi. Okay, so what is this? Let's work it out. So there's a bunch of terms in here. Again, remember d mu is partial nu plus I e a mu. Okay. So there's a term here which is the commutator of the partials, right? There's a term here which is IE times partial mu a nu minus partial nu a mu acting on psi. Okay. And now if you work out what this is, this turns out to be i.e. partial mu a nu minus partial nu a mu acting on psi. So notice the commutator of covariant derivatives acting on psi isn't a derivative at all. It's just a number, okay? Just a function of this field A multiplying psi. And this number is actually important. Let's give it a name. We're going to call this IE times F mu nu, where F mu nu is called the field strength tensor. Okay, and it's defined like this. Mu nu is the field strength tensor. Okay. So, I see, sorry, there's a question. The question is, sorry, can I get a reminder? How did gamma mu come before d mu? Very good. So, really, I just basically just made this up, okay? So, if you remember the normal Dirac action, the Dirac action that we know and love from before has gamma mu multiplying partial, right? So this term, if I expand, oops. So this term, if I expand it out, is psi bar gamma mu partial mu minus m. And now what I'm doing is I'm taking the partial derivative and making it into this gauge covariant derivative. Okay. And so the gamma mu is still there because it was there before. That's all that's happening. All right. Good. Good question. Other questions? Another question is that I have a question. What does it mean physically that the mass term of the Dirac theory is U1 invariant locally? Does the existence of the partial derivative in the Dirac Lagrangian break the local U1 invariance? Is the covariant derivative responsible for restoring it? How can we know the gauge field is really electromagnetic field? Is it by transmission behavior or anything else? Yeah, these are all great questions. So in a nutshell, what does it mean physically the mass term Dirac theory is U1 invariant locally? Again, all these what does it mean physically questions are tricky. I don't think it means too much. It just means that it doesn't involve derivatives, so it's easy to make it gauge invariant. Okay. The covariant derivative is responsible for restoring it. That is correct. Without the covariant derivative, you cannot take derivatives of the Dirac field in a U1 gauge invariant way. And how do we know the gauge field is the E&M field? That's because we write down the theory, we look at what happens, we look at these predictions, and then we compare that to experiments. And we're like, oh, yeah, that's what happens in experiments. That's how we know that it's the E&M field. Okay, so it's really because of experiments. Excellent questions. Another question. This is called the minimum coupling principle, right? I think so. It's called the minimal gauge coupling, possibly. Typically, there's actually kind of a unique way to do this. Yeah, but you can call it that. Another excellent question. Is there a relationship between these covariant derivatives and the one in general relativity? Yes, there is. Students who have studied general relativity will be familiar with what we're doing. We are trying to take derivatives of something, and the naive way of doing it doesn't work. And so you have to introduce a new field to fix it. In general relativity, you introduce something called the Christoffel connection. Over here, we introduce a gauge field, but you could call it a gauge connection if you want to. It sounds a bit more intimidating that way. Okay, very good. And the final question, another question is general relativity a gauge theory? There's a sense where you can think of it as a gauge theory of translations. That's correct. That sense is sort of not extremely useful because that, in my opinion, obscures the geometric character of it. Yeah. Yeah, so general relativity can be thought of as a gauge theory of the Lorentz group in some way. But again, this sort of obscures this. GR is nice because you have this manifold and the manifolds wiggle around, and it's a bit hard to see in the gauge theory picture, but you can think of it that way formally. Yes, that is correct. It's good for some purposes. Yeah. Okay. All excellent questions. All right. Thank you for all these questions. So the connection to GR will actually become a bit clearer in about half an hour when we go to non-abelian gauge theory. All right. Okay. So, but let's run this. So what have we done? We have started with a Dirac Lagrangian. We made it locally gauge invariant. We ended up with a new field A. And now we've constructed a field F, which is this derivative of A. And now this F mu nu is gauge invariant. Okay. And how do we know that it's gauge invariant? Well, purely abstractly, we know this. Okay. So F mu nu must be gauge invariant. Okay. And why? How do we know this? It's because we have that the commutator of d mu d nu acting on basically this commutator we just checked is equal to IE F mu nu. And now what you can imagine doing is take this equation and act on with psi on both sides, okay? And then do a gauge transformation. And what happens? This is just a number, okay? So you get IE F mu nu e to the I lambda times psi. And over here, we constructed this thing to transform nicely under gauge transformations, which means that the e to the I lambda comes out on the left-hand side. Okay. And so we see that this equation makes sense if you can just take the lambda through without changing the f, which means that F mu nu must be gauge invariant. Okay. Now, of course, we could have seen that in a much simpler way, because you know that under a gauge transformation, A mu just goes to A mu minus 1 over E partial nu lambda. And so it's very easy to see that if you do a gauge transformation of A here, then this A will transform, this A will transform, and what you will get left over is a piece like partial mu partial nu lambda minus partial nu partial mu lambda, and these guys cancel because it's the same set of derivatives and partial derivatives commute. There's a very direct way to see that F mu nu is gauge invariant, but this abstract way of thinking about it will again be useful in about half an hour. Okay. Okay. So now that we know how to take a derivative of A, you can also check that, by the way, d mu A nu by itself is not gauge invariant. You have to take this F combination if you want to take a derivative of A. Then we can now write down the most general gauge invariant action involving our friends A and psi. So let's write down the most general gauge invariant action. Well, it's not the most general, but let me say the most general. Okay, I'll qualify this in a second, but so what can I do? I can write down a term like this with F mu nu. I can write down a term like this with D and psi. Okay. And now I could write down some other things, but all those things will involve more products, Like, for example, you could write down F mu nu, F mu nu, F mu nu, F mu nu, or something like that. This is gauge invariant, but it involves 4 Fs. Okay, so it involves a lot of Fs. So if you restrict yourselves to the minimal things, then this is the most general action that you can write down. it turns out it's the most general action that is what's called renormalizable. You don't know quite what that means yet, but there's a good reason to think only about this sort of action. Okay. So this action is, of course, exactly the action of quantum electrodynamics. So this is the action of QED. In other words, the action of electromagnetism coupled to electrons. Where the electromagnetism comes from the part involving A, and the electrons come from the part involving psi. Okay. So, for example, here's the sort of thing that's important from gauge invariance. For example, we cannot write down a term like plus m squared a mu a mu. All right. For example, a mass term for the gauge field. We cannot do that, right? Because this term is not invariant under gauge transformations, right? So this term is forbidden by gauge invariance. So that's an important thing. So for example, you might wonder, the photon is massless. Why is the photon massless? Why is there light? In some sense, it's related to the fact that you can't write down this mass term for the gauge field. Okay. I say related because this is actually a big story and I'm sort of skipping some important details here. Okay. But for example, the mass term is forbidden. And this is basically the most general action you can write down that's important at low energies. Okay. Okay. There have been some questions. Let me answer some questions here. So there's a question: why does this construction of gauge theory seem so artificial? Is there a way in which all this is natural? And again, artificial and natural are, I think, subjective notions. I think there's a deep question as to what is the meaning of gauge invariance, and different scientists with different opinions on this. This again might sound a bit artificial, but it turns out it is correct. This is the principle that describes nature. Okay, so that's an important thing. And there are ways to motivate this that we can talk about. They're all a bit more advanced though, so I don't want to get into them right now. I'll be honest, this is what I think about in my research. I think about why gauge symmetry exists and what it's good for. And I have very strong opinions on it, but I don't want to inflict them on you right now. What if F is not gauge invariant? Does it make it a potential rather than strength? Yeah, good question. Normally when we say gauge potential, then that means that it's something that transforms under a gauge symmetry. And field strength refers to something which is gauge invariant. So indeed, if F was not gauge invariant, I wouldn't call it a field strength. I'd call it a potential instead. But more importantly, if F was not gauge invariant, I couldn't write down this action, okay? Because everything appearing in the action, I want it to be gauge invariant. All right, so that's more important than the name, is the fact that I want to use F to write down an action. Okay. Next, going down the list of questions. Is Lorentz invariance related to gauge invariance? No, not really. They're different things. You can have Lorentz non-invariant theories that are gauge invariant. They come up in condensed matter physics. You can have gauge invariant, things like that. So I wouldn't say they're really related. They're just two different forms of invariances. There's a question. How do we restore the gauge invariance for a Proca field with mass? So the truth is, there's multiple ways to think about this. If by Proca field, you just mean a field like this, m square a, like a field where you just add a mass term like this, then you cannot restore the gauge invariance. Okay, it's just not a gauge theory. Okay, it's a theory of a massive vector field and not a gauge theory. Now, there is something else you can do, which is you can sort of write what's called a Higgs theory or a Stuckelberg theory. And that is a gauge invariant theory that involves a massive gauge field. Okay. These two things are subtly different. And I confess, I don't remember quite which one Proca refers to here. But basically, you invent a new field, which it looks like this. You write a term like this for the Proca field. And this is called the Stuckelberg mechanism. This theta absorbs the gauge invariance. Again, this is a bit advanced, so I don't want to get into this, but it'll come up a little bit when you do the part on the Higgs field with Gonzalo in a few weeks. Okay, good. Could I explain again what a computation that derived F? Yeah, so I'll do it again in the non-abelian case, actually, but the basic idea is just the commutator of two covariant derivatives is a nice thing to think about, okay? It gives you this nice answer. I dropped the psi here, sorry. It gives you this nice answer, and it's a thing that has to transform nicely. Okay, it's an easy way to derive gauge invariant objects. That's really the point of this. And you can go through this on your own time and check that this makes sense, but I assure you that it does. And we'll do it again in the non-abelian case in a second. Okay. So thank you for all the questions. I want to keep going because again, we have very little time. But I'll keep going. Good. So yeah, indeed. There's some other questions. I'll discuss I'm gonna delegate the more advanced questions to the end of the lecture so I can discuss them in detail without feeling guilty that I'm missing the main points. Okay. Thank you. So now let me okay, just to stress that this is the action of QED. Okay, so you can start with this and you can derive all of the physics of electrons coupled to photons. Okay, and I should say this is most of the physics of almost everything we see around us involves electrons coupled to electrons and protons coupled to E&M, like chemistry, the whole field of chemistry. All these things are basically you can derive, you can't derive them, but they're all determined by this very simple action. So it's kind of a deep thing. Okay. Okay. Now let's study some aspects of this. So for now, I want to just discuss some aspects of the Maxwell part, of the E&M part of this action. Okay. So let's just discuss some quick aspects of this. So I'm just going to talk about this action, which I'm going to call the Maxwell part of the action. And this is integral d4x minus 1/4 f mu nu f mu nu. Let's talk about this a little bit. Okay. So first, what is the classical equation of motion of this theory? You've done this in a few weeks ago. The equation of motion is just d mu f mu nu equals to 0. All right, you can get this, vary this action, and you can derive this equation of motion. Okay. Now, this is of course the same as Maxwell's equations. It's like curl of E minus, wow, I forgot the signs. Something like this, dB dt equals 0. There's a way to do this right. Okay. Now, I want to point out an interesting fact about these equations of motion, how they're different from other equations of motion that you might know about. So we also had the Klein-Gordon equation for a scalar field. Remember, that was partial square phi equals to 0, right? So the Klein-Gordon equation. Now, there is a difference between these two equations, and I want to explain what it is. The Klein-Gordon equation, this equation here, defines what's called a well-posed Cauchy problem. And what does that mean? What that means is if you imagine that you have some time, let's call it t equals to 0. And now suppose you specify the field. Okay, so I specify at phi t equals to 0 and all x, I specify this field. So it's something that we know. We know what it is. Equals to some, let me call it psi of xi. This is known. Okay, that says known. And we also specify the time derivative of phi at this point. Let me call this psi prime of xi. If you specify these two things, then what you can do is you can solve the equations of motion to figure out phi of t and xi for all later times. Okay. In other words, once you know the field at one time, you can figure it out at all later times. This is time. And this is important. This is the whole point. What this means is you can predict things. The point of physics is that if you know what's happening at one time, you can predict what's happening later. And this equation lets you predict things for phi. Okay. Now, this equation is different. This equation is not of the same character. You see, the fundamental degree of freedom here is phi, and the fundamental degree of freedom here is actually A, because you varied this Lagrangian with respect to A, the gauge field. And it turns out this equation does not define a well-posed Cauchy problem for A. Okay. So d mu f mu nu equals to 0 is not well-posed for A. All right. Now, you can figure that out by staring at these equations. Like you can write down the equations and look at them, and you can figure out that this is true. But there's a sort of very easy way to see this, right? Which let me just explain how to see this. If, for example, if you have some field configuration, A mu of x, which solves the equations of motion, d mu f mu nu equals to 0, then it's a fact that A mu of x plus a gauge transformation, d mu of lambda x, also solves this equation, right? Let's just check why. We take this guy and we plug it into here, but of course f doesn't care about this piece at all, so f is exactly the same. So let me call this guy A mu bar, all right? So A mu and A mu bar are both solutions to the same wave equation. Now let's just pick lambda of t and x. Let's say that it's 0 near t equals to 0, and it does not equal to 0 at late times, at late t. Okay. In that case, I'm going to have two field configurations, A mu and A mu bar, which start out being the same, if this is near t equals to 0, and then they change later on, right? So here's A mu bar, here's A nu. They're different because for later times, this lambda kicks in and makes these two guys different, but they both solve d mu f mu nu equals to 0. Okay, so what does that mean? You know, what does that mean? The point is that these equations do not let you solve for the movement of A, okay? They do not uniquely fix the movement of A. So this might seem sort of very bad, right, from the point of view of predicting things, because the point of physics is to predict things, and I've just shown you that we cannot predict the movement of A, okay? You don't know what it's going to do. Just strictly mathematically, the equations of motion have multiple solutions. And so what we do, how do we solve this? What we do is we say, so the resolution is anything which is not gauge invariant, oops, ran out of space, is not physical. Okay. And you can see we really need something like this, right? We have to impose something like this because things that are not gauge invariant, for example, A, we can't even predict how they're going to change with time. So if they're physical, we'd be in big trouble. But instead, we're going to say they're not physical, and so it doesn't matter that we can't solve for them. Okay. What we only care about is gauge invariant things. So for example, f mu nu and so on. Okay. F mu nu is gauge invariant, and we can solve for f mu nu. Okay. So gauge invariant things are okay. Gauge non-invariant things are not okay. And this problem becomes even worse in the quantum theory, as we'll see. All right. Okay. So there's a question. Let's see. There's some more questions. Let's see. Intuitively, why exclude non-gauge invariant fields from being real? Intuitively, it's really just because if it's not gauge invariant, we don't know how to solve for its time dependence. Okay. For example, A mu is not gauge invariant, and I can't even tell you what it will do at later times. All right. We cannot solve for their time dependence. They are not predicted by the physical theory. That's really the reason. There are worse problems actually still, but this is, I think, the simplest way to see that you need something to go, you need this to be true, because even in the classical theory of gauge fields, it doesn't make sense if you insist on the gauge potential being a real thing. Okay. Good. Okay. So now we're doing okay on time. So if I know exactly what you've done, normally if I was teaching this, I would now solve this equation explicitly. Okay, so we have d mu f mu nu equals to 0. You can solve this equation explicitly, and what you find is that there is a there's a photon which propagates like this. So you can basically, you write something like a mu equals to epsilon nu e to the I omega t plus ik z. And then you can show from the equations that omega equals to k for the photon, which means that there's a massless particle. Sorry, there's a massless wave, not particle, which is the electromagnetic wave. Okay. So you've all done calculations like this, I think, earlier in this course, and they're quite simple to do. So if you haven't, then I encourage you to just take this, plug it into here, and see what happens. All right. Okay. But I'm going to now move on to how to quantize this Maxwell theory. Okay. So far everything has been classical. Now we're going to do a little bit of quantum Maxwell theory. And after that, we'll take a short break. Okay. So to quantize Maxwell theory, the best way to do it is to do it with the path integral. Or okay, best is again subjective, but the way I like to do it is to do it with the path integral, which you learned about. So write it in the following way. So what we do is we do a path integral for A. And now let me work this out. So the path integral involves doing some sort of integral over all of the fields. So we do an integral over all fields like this. And the thing that we do the integral over is the exponential of I times integral d4x minus a quarter f mu nu, f mu nu. Okay. And we do this path integral. Okay. Now, let me simplify this a little bit. So this is basically partial mu a nu minus partial mu a nu times partial mu a nu minus partial mu a nu. And I can simplify this more and write it like 2. So let's see, there's a minus 1/4 here. And now I can write it in the end like a half. There's a little bit of algebra here, which you can do. I encourage you to check. It becomes partial squared eta mu nu minus partial mu times a nu. Okay. So this is just the Maxwell part of that action. Okay. There's a question. We are recording. Yes, that's correct. Everything is recorded. Yeah. Okay. So okay, this is what we have. And now the question is, how do we do this functional integral? How do we do the path integral? If you remember last time, the way to figure out the propagator, the Feynman propagator for the field that you're path integrating over, is to take the thing that appears in the action in the kinetic term and invert that thing. Okay. So we want to invert this operator. To find the propagator for the Feynman, for the photon field. Okay. Now, how do we do that? Let's remind ourselves how we do that. Last time we did this by basically going to momentum space, which means that we replace every derivative with a p. You know, we do a Fourier transform, then we go to momentum space, and every partial derivative becomes a momentum operator. And so what that means is we want to invert this operator. P squared eta mu nu minus p mu p nu. We want to invert this. Okay. There's a problem with this operator. Does anyone know what the problem with this operator is if we want to invert it? Can anyone see what the problem is with this operator? This is, if you've not seen it before, it's hard to see, but you see, this operator has no inverse. Okay. To see that, let's just consider acting with this operator, p mu nu minus p mu p nu, on the vector p nu. Okay. What do we get? If we try to do this, then what do we find? From the first term, we have p mu times p nu. From the second term, we have p mu times p squared, which is 0. In other words, this operator has a 0 eigenvalue. Has many, in fact, many 0 eigenvalues. And an operator with a 0 eigenvalue cannot be inverted because everything in that direction is killed. And so you cannot invert it. And so this is terrible. It means that it looks like we can't invert this operator. Okay. Now, I'm doing a terrible thing here, which is that I'm telling you about a problem, and I'm not really telling you how to fix it. Okay. There's a way to fix it. Okay. And the way to fix it is called the Fadeev-Popov procedure. And you can read about it in the references of the lecture notes online. And once you fix it, basically the point of doing this fixing, this Fadeev-Popov fixing, is that it gets rid of the configurations that you don't like in the path integral. So the reason why this is happening is that a configuration that looks like this, that looks like a pure gauge configuration, a configuration that is just d mu of lambda, this thing leaves f invariant. So f is 0 for all these configurations. And when you path integrate over all those configurations, you get all kinds of things that don't converge and just all sorts of gibberish. And we need to find some way to get rid of these gauge transformations in this thing. The Fadeev-Popov has taught us how to do that. And following that procedure, you can find a propagator. And I'm just going to tell you what the propagator is. And again, if you're interested, you can look in the references to see how to derive it. It takes me normally about an hour to do this calculation on the board, but it's a well-posed calculation. Path integrals are crucial for this calculation. Okay. But if you go through this, you find that this is the propagator, or the Feynman propagator for a mu. Okay. Let's talk about it for a second. There's a thing here called zeta. And zeta is called a gauge fixing parameter, and its value doesn't matter. You can set it to whatever you like. And so normally I set it equal to 1 because then that kills this term and then life is simpler. Okay. And notice this has a p squared over here. You should compare this to what you saw for the Klein-Gordon field where you had an I over p squared minus m squared. That means that the m here is 0. There is no mass. And the fact that it's just a p square means that this field, this particle associated with this, which is of course called the photon, is massless. Okay. And now with this guy, you can calculate everything you like. Okay. I won't go through it in any great detail, but again, you can look at the lectures, the lecture notes, and you can see that from this thing, you can calculate everything that you like in the theory of QED. Okay. So we're now going to take a short break for about 10 minutes. But before we do that, I'm going to make an announcement of actually, Raki, are you here right now? Or Raki, can you? Great. Okay. Okay, everyone. Hello, welcome back. I hope you could all access the form. Now, let's now move on. So what we just did in 1 hour was abelian gauge theory. Okay. In the next hour, we are going to do a very whirlwind tour of non-abelian gauge theory. Okay. This is a very powerful generalization of the previous idea. And it turns out these play a very important role in the standard model. In fact, the non-abelian gauge theory, this theory of the strong interactions turns out to be a non-abelian gauge theory with gauge group SU3. And the theory of the weak interactions is a gauge theory with gauge group SU2. So I should explain what that means, what is a gauge group, and so on. So first, before doing that, what is a gauge group? We're going to take a second and do a little bit of math and understand what is a group. So this is group theory in 1 second, or okay, it's going to be like maybe 10 minutes. Okay. So a brief recap of the minimum group theory that we need. So what is a group first? Okay. A group G has elements in it. Okay, so a group G is some set of elements, which we can call them G1, G2, G3, and so on. So these are all elements of the group G. Okay. And if it's a group, then there's some way to combine two elements to get a third element. So the definition of a group is that there's some way to combine, for example, G1 and G2 to get some third element, G3. All right. And the point is that if G1 and G2 are in the group, if G1 and G2 belong to the group, then that means that G3 also belongs to the group, okay? So anything that has objects and ways to combine the objects to get another object is a group, provided there's some technical considerations. So for example, there must be an identity element in the group. There must be a way to take inverses of elements in the group and so on. I'm not going to really go on into that any detail. It's going to be sort of common sense for us that this is the case. But this is the meaning of a group. So I should just, the mathematician in me is a bit upset at this. Let me just say that there also exists the identity element 1 and inverses. Okay, now the mathematician in me can be at peace. And let me give you some examples. So here's some examples. So there is the group U1. So what is the group U1? The group U1 is generated or consists of numbers e to the I alpha, okay, where alpha is a real phase, which means that e to the I alpha, alpha is a real number, which means that e to the I alpha is a pure phase. Okay. So this set, the set of e to the I alpha, such that alpha is a real number, is the group U1. And let's just check that it's a group. For it to be a group, we need to have a way to combine two elements to get another element. And for us, this combination is just the product, right? So what you do is you take two objects, e to the I alpha 1, e to the I alpha 2, you just multiply them together, all right? And you get another object out e to the I alpha 1 plus alpha 2. And if these guys are in U1, then this guy is also in U1, okay? Now, let me point out an important fact. The order in which we took this product doesn't matter. In other words, we would have gotten the same answer if we had done alpha 2 times alpha 1 instead of alpha 1 times alpha 2, right? These are the same. The 2 and the 1 are flipped here, but you get the same answer either way. And this fact, if the group operation is commutative, in other words, doesn't care about the order, that means this kind of group is called an abelian group. All right, so this is an abelian group, U1. Okay. Now here's another example. Example number 2. Consider the group SU2. Okay. So what is SU2? SU2 is defined to be the set of 2 by 2 matrices that are unitary, and with determinant equal to 1, okay? Here the U stands for unitary, and determinant 1, S stands for special, and special means determinant is 1 in this case, okay? So this is a set of objects, 2 by 2 matrices that are unitary with determinant 1, all right? Now, so for example, there's again a group operation, which is that we take, for example, U1 and U2 to be elements of SU2. Okay. And then you consider their matrix product. So you do U1 times U2, where this now is a matrix product, and this is equal to U3. Okay. And this product will also be in SU2. If U1 and U2 are in SU2, then so is U3. Let me just remind you, by the way, unitary means that U dagger U equals to 1. This is the definition of unitary. Now, there is, however, a very important distinction here, which is that this group, the group operation is not commutative. In other words, generally, U2, U1 is not equal to U1, U2. Okay. The group operation is not commutative, and this kind of group is normally called a non-abelian group. Okay. good notation, right? This is abelian. This is therefore non-abelian. Okay. Now, I want to try to give you an example of why this is non-abelian. So, first of all, the truth is everyone is very familiar with the group SU2, whether you know it or not, because SU2 is locally in equivalent to SO3. So local rotations in SU2 are the same as rotations of SO3. And SO3 is the group of rotations of three-dimensional objects. So every time you move things around in 3D, you are moving in some space in SO3, and maybe you're moving in SU2 as well. So the fact that this group structure is not, that the group is non-abelian, you sort of know this about everyday life. So for example, if I take this pen and I rotate about one axis and then about the other axis, or if I do it the other way, so if I rotate first about, so what did I do? I rotated around this axis and then this axis. If I do the order the opposite way, so I rotate about the other axis first, actually first nothing happens because I'm rotating around this axis and that leaves the pen invariant. And then this rotation gives me this. So it's quite easy to check that the composition of rotations in normal three-dimensional life, the order matters. You just know about this already from everyday life. And this is the same as saying that the group is non-abelian. Okay. Okay. So what we did in the first half of today's lecture was we built a gauge theory for the abelian group U1. Now it turns out that you can build a gauge theory for any group. Okay. So you can build a gauge theory for any group. Okay. And so for the rest of this, we're going to construct a gauge theory for a non-abelian group. In other words, we're going to construct a gauge theory for SU2. Okay. I'm going to do it for SU2, but it turns out that I'm going to try to make the formulas general enough that it'll work for any SU, any SUN, but you'll see that as we go. Okay. So what is going to happen? The idea that we started with was that we had our field psi, and we demanded that psi be invariant under something like this, right? Where this e to the I lambda x was a space-time dependent U1 group element, okay? So that was for the U1 group. Now we're going to do it for the non-abelian group. So what I'm going to demand is that psi of x be invariant under a rotation like this. I want psi of x to be invariant under some u of x multiplying psi, where this u of x is some SU2 element who depends on space. Space-time. Okay. And this is a 2x2 group element, which means that I need my psi field to be a two-component object. So this psi is going to have two components that are acted on by this SU2 matrix. Okay, so I'm going to take this SU2 matrix U and act with it on psi. Now it has two components that are rotated by this SU2 matrix. It also has some spinner components that I'm not going to talk about. But remember, it's a Dirac spinner, so it has some spinner components. Those aren't important for this discussion, so I'm just not going to write them down. Okay, but they are there. Okay. So now to proceed, I first need a way to talk about an SU2 element. And again, people have studied this, I think, in their course in basic quantum mechanics. So how do I write down, how do I parameterize an SU2 element? The way we do this is just through this Pauli matrices. So an element of SU2 looks like this. You can write an SU2 element as U equals to exponential of I alpha A TA, where A here runs from 1 to 3. Okay, so alpha A is just a set of numbers. Okay, so the alphas are numbers. And the T's are matrices. The TAs are matrices, which are actually the Pauli matrices, half times the Pauli matrices. So let me just be quite explicit about this. The Pauli matrices are T1 equals to 0, 1, 1, 0, half. T2 equals to a half 0 minus I 0, and T3 equals to a half 1 0 0 minus 1. Okay. So what I'm saying is, for any choice of these alphas, take the matrix exponential of the alphas multiplying these three t's, you will get some matrix out, and that matrix will be an SU2, which means that it will have determinant 1, and it will be unitary, so its dagger will be equal to its inverse. That is a good thing to check. Check that this works. This is a good exercise. I should have made it a homework problem, but I didn't. Okay. Okay. Now, the t's have the following property, which again, you remember from your quantum mechanics class. If you take the commutator of two t's, Ta and Tb, then it's equal to I times, I'm going to call this FABCTC, where F is a set of numbers, and in our case, FABC is just epsilon ABC, where this epsilon is the totally antisymmetric Levi-Civita symbol. Okay, so epsilon is antisymmetric in all the indices, and epsilon 0, 1, 2, epsilon 1, 2, 3 is equal to 1. Okay. This is the regular commutation relation of the sigmas. We're not really going to need this for any great thing, but every once in a while I will need it, and so I'm just putting it here. Okay. Okay. And now we now can construct our gauge theory. So the point is, we have a field psi, which transforms in this manner. And I want to write down a theory which is invariant under this kind of non-abelian gauge transformation. Okay. Okay, so let's do it. Let's try to first write down, let's take the basic attempt. Okay, so we're going to do the same thing we did before. We try writing this down. So let me just try to write down something like integral d4x psi bar I d slash minus m psi. Okay. Now, again, we're going to run into the same sort of problem that we had before, right? So let's first think about the term with the mass, okay? So under the gauge transformation, psi goes to u times psi, and psi bar goes to u dagger. This is u of x, u dagger of x. And so the mass term is okay, right? In the mass term, the u will cancel against the u dagger, and because u dagger u is 1, this mass term is already invariant. But the derivative is going to cause problems again, just like before, right? And we now need to fix that problem again. So what did we do last time? Last time we invented a field that solved the problem for us. So we're going to do the same thing here, but first we need a demand. We're going to try to invent a non-abelian covariant derivative. And the non-abelian covariant derivative is going to transform. We're going to have d mu psi goes to d mu prime psi prime. Okay. And we're going to demand that this thing transforms like u of x times d mu psi. This is our demand. Okay. And this is, again, you should remember, this is very similar to what we had before. Before we had d mu psi went to e to the I lambda times d mu psi. This is the same, except that instead of having an e to the I lambda, we have some matrix u acting on this. Okay. Okay. So we're going to again, and so by the way, this statement that it transforms like this is called transforming homogeneously. This is some lingo you will sometimes see. What homogeneously just means is it just means it transforms nicely with an overall u on the left-hand side with no extra plus d mu lambda pieces floating around. Okay, so we are going to need a new object. We're going to need a new field, a new gauge field. We will need what's called the non-abelian gauge field. And that object is going to be called A. It's going to be a vector field again, A mu, with an extra index A. Okay. This little a, again, runs over 1, 2, and 3. It runs over the 3 dimensions of SU2. Okay. This is what this little a runs over. So we actually have 3 different gauge fields, each of which is a vector field. Okay. Okay. And now we have a way to construct the gauge covariant derivative, d mu psi is defined to be partial mu psi minus I g a mu a t a acting on psi. Okay. Let's just think about this for a second to make sure this makes sense. Psi here is a two-component object. Okay. Partial mu psi is partial mu psi. This thing here says we have three vector fields, sum over all the indices of the vector fields, and multiply each of the a's with the corresponding t. This t is a matrix, and that matrix multiplies this two-component object. All right. That is what this formula means. And this is the non-abelian gauge covariant derivative. Let me remove these circles. They look ugly. Okay. Are there any questions about the non-abelian gauge covariant derivative before we go on? This will make sense. Sorry, there's a question. Are SU2 invariant gauge theories called Yang-Mills theories? Yang-Mills theories are more generally gauge theories for any non-abelian group. Yeah. So SU2 is a specific case of a Yang-Mills theory. That's correct. Yeah. Is G called weak hypercharge? At the moment, G is just a name for the coupling. I would call it the gauge coupling. In the context of the standard model, there is something related to G, which is related to the weak hypercharge. But normally the hypercharge is actually a property of the field and not of the gauge group. I'm going to advise you to ask that again to Gonzalo when he does the standard model course, because I don't want to take away his notation. But it's related. Yeah, it's related to the hypercharge. Yeah. Good. Other questions? Okay. And then are there any proofs corresponding to new covariant derivative? Okay, excellent question. Let's prove something about the new covariant derivative. Let's prove that it does what we want it to do. Okay. Rather, we're going to derive the transformation property of the gauge covariant derivative. Okay. So we need to see what we need A to do in order to satisfy our demand. This is our demand, remember? So how do we make A satisfy our demand? So let's work out everything. So for example, let's compute d mu prime on psi prime. Okay, so what is that? That is partial mu minus ig a mu a prime ta acting on psi. Sorry, on psi prime. Psi prime, of course, is u of x acting on psi. Okay, and well, now we work this out. What is it? Let's do it carefully. We have d mu u acting on psi plus u of x partial mu psi, okay, minus ig a mu prime a ta on u of x acting on psi. Okay, so I just expanded this out. And now the demand, here is the demand, is that this be equal to u of x d times psi, which is partial mu minus g a mu a ta acting on psi. Okay. So now we can see what's happening, right? Some terms look similar. This term is the same as this term. But notice there's a crucial difference that now the u is on the right-hand side of the t in the top line, and the u is on the left-hand side of the t on the bottom line. And because this is non-abelian, they don't commute anymore. In the abelian case, I just took this through without worrying about it, but now I can't do that anymore. Okay. And so what we find is a slightly more complicated expression. If we now equate these two lines and ask what we need a mu prime to do, then we find that we need d mu u minus ig a mu a prime tau equals to u minus ig a mu a ta. So again, the u is on the right-hand side here and on the left-hand side here, but we can still solve for a. So we can solve this for a mu prime. And what we find is that a mu a prime ta equals to u of x times a mu a ta plus I over g partial mu u dagger of x. Okay. So what did I do here? Basically, the point is I just figured out this a mu by itself. So I hit this thing from the right with u dagger u equals to the identity. So that gets rid of the u from here, and it gives me an extra u dagger here. And then I move this around and did some manipulations. Okay, so you can easily check that this implies that. Okay, so because some stuff happened, let's just remind ourselves. What this is saying is that if you do a gauge transformation parametrized by u, which is a space-time dependent SU2 element, then the gauge field, the non-abelian gauge field, transforms in this manner. The new one, a mu a prime, is related to the old one by this formula. All right. Now, this is the most general formula. It's a little bit hard to visualize, I find. So I want to sort of do a slightly more simple thing, which is this is the most general formula, but let's also now imagine for an infinitesimal rotation. So imagine that we take u of x to be equal to the exponential of I alpha of a times x ta, and then take alpha a to be small. Okay, which means we're looking at a very small rotation, an infinitesimal rotation. Okay, so the field, if this was the field to start with, then afterwards it just rotated a little bit, in a way that depends on space, but it's always a very small rotation, something like that. Okay. Then what you can do is, what this means is basically you take this and you expand it out, like, expand out the exponential. So it's like what, 1 plus I alpha a of x ta plus blah, 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 where these are terms order alpha squared. And then you can just drop all of these because alpha is small. Okay. And then what you can do is take this and plug this into here, and then solve for a mu explicitly in terms of these alphas. Okay, so again, for lack of time, I won't do it explicitly, but you can do this. And what you find is, so plug in and solve. Again, this is a good exercise, which is worked out in the notes. Then what you find is that you get something like this. You get that a mu prime a ta equals to a mu a ta plus, and now here's an interesting thing that happens. The terms assemble so that you get something like this. There's a term involving a TB and a term involving a TA, involving the commutator of these two matrices. Okay. And then you have a term like this here. Okay, this comes from here. It basically comes from this term here comes from expanding out this, expanding out this. This u has an e to the I alpha. This u dagger has an e to the minus I alpha. And then if you expand out all the pieces, then you end up getting a commutator here with the alpha, the sign of the alpha differing between those two terms. All right. And then remember, we have a formula for the commutator of the t's. Formula was here. This formula right here. So we can use that and then do some more work. And what we find after yet more algebra is that a mu a prime equals to a mu a plus f abc a mu b alpha c plus 1 over g partial mu alpha c. Sorry, alpha a. Okay. And so this is the infinitesimal non-abelian gauge transformation. Okay. So let's take a second and stare at this. So first of all, remember the transformation is parameterized by the alphas. The alphas are telling you how much you rotate this field in this non-abelian way. This last term says that the shift in A mu is just d mu alpha A. So this last term here looks just like an abelian gauge transformation, right? But this term is different, right? This term is saying, one way to think about this term is that it's telling you that you rotate this field in some way. When you work with this alpha of C, you do a gauge transformation, then A is altered in some manner. Now, I want to give you some intuition about what this extra term does. So let's imagine that in the case of SU2, which is the one we're thinking about right now, these ABCs, there's three of them. And so you can imagine that A mu A, let me just suppress the mu index for now because it's not doing anything in this formula. You can imagine that A mu is a vector in R3, where this A runs over 1, 2, and 3, right? So you can imagine it's a vector in R3. And this FABC is epsilon ABC. And so the way to think about this particular term is that this is saying that delta A viewed as a vector in R3 goes like A cross alpha, where we are again viewing alpha now as also as a vector in R3. Okay. So what this is saying is that if you do a non-abelian gauge transformation with some alpha, this rotates the non-abelian gauge field about that alpha. That's the way to think about this thing. This cross product is exactly telling you that. Okay. Okay. And now, finally, just one more notational thing. Sometimes I'm going to write A mu with no superscript. If I just write A mu by itself, then that means A mu ATA. Okay. So in other words, this is a matrix that's gotten from these matrices. Okay. Now, any questions about this? I'll take one or two questions if there are any before very, very quickly to construct the Yang-Mills action. Again, very fast. There's a question about renormalization techniques. Let me answer that at the end. Let me answer that at the end. It's a good question. It has a good answer, I think, but it's not directly related to non-abelian gauge theory. So I'm going to leave it to a little bit later, if that's all right. Yeah. Please ask it again at the end. Any other questions? Okay. Why do we need non-abelian gauge theory in a physical perspective? Well, this is a good question. I think it came from, I mean, it's really because it agrees with experiment. That's really why. Like, it's a fact that the theory of the W and the Z particles, that is described by non-abelian SU2 gauge theory of the sort that we are constructing. That's a fact. You know, also the same with SU3, the theory of the proton is a composite of three particles called quarks. And the thing that holds them together is an SU3 gauge field of this sort. So we definitely need non-abelian gauge fields from that point of view, because it's the correct thing to describe the experiments. That's really why. Yeah. Okay. All right. So okay, good questions. Let me press on and finish constructing the theory, and then I'll take some more questions. So what have we done? We have made a gauge field, and we have very quickly derived how that gauge field transforms under a non-abelian gauge transformation parametrized by alpha A, where alpha A is some space-time dependent non-abelian gauge transformation parameter. Now, the next thing to do is to write down a kinetic term for this. In other words, I want to write down an action which is invariant under non-abelian gauge fields. And this is tricky, all right? Because if I just take a derivative of partial mu, A nu, A, this is not gauge invariant. And it's much worse. The problem here is really much worse than in the abelian case. In the abelian case, I could just pretty much see, okay, d mu A nu minus d nu A mu, that's going to be gauge invariant. Here, because of this extra term, the problem is pretty bad. I don't know how to immediately solve this. And the way to do it is what we did in the U1 case, the way to construct, we need to construct the non-abelian field strength, which is a gauge invariant combination of derivatives. So we need the non-abelian field strength. And the way in which we're going to construct that is by looking at the commutator of two non-abelian gauge covariant derivatives on d mu psi. Okay. And now you can work out what this does through construction. You just compute the commutator and do some algebra. And it turns out that when you do this, then the final object, okay, should be thought of as being a matrix that acts on the field psi. Okay. This is, again, just like the U1 case. We took the commutator and we found that the answer was something called F mu nu acting on psi. We can do the exact same thing here and figure out what F mu nu is. And again, there's some algebra, which I will not do in any detail. But if you work it out, which again, you can do, what you find is that F mu nu A is equal to d mu A nu A minus d nu A nu A plus G A mu B A nu C F A B C. Okay. So this is the non-abelian field strength. Okay. So let me just again tell everyone what is happening here. It is a tensor. It's an antisymmetric tensor. It has a mu and a nu index. It also has an A index, meaning that there are three components, okay, of this. A runs from 1, 2, 3 for SU2. This part here was already present in the abelian gauge theory. This part here is new and comes from the non-abelianness of this thing. All right. You need this because without that, this thing is not gauge invariant. And you can check that under a gauge transformation, F mu nu transforms like this. So I shouldn't say that it's gauge invariant. What it is now is that it's gauge covariant, meaning that it transforms in the following way. If you do a gauge transformation, then F mu nu A T A goes to F mu nu prime A T A, which is equal to U of X times F mu nu A T A times U dagger of X. Okay. This is how F transforms under gauge transformations. Okay. And I have not proven this for you, but you can check for yourself from this idea. Let me just tell everyone why this works. Because D transforms nicely under a gauge transformation, meaning that if you do a gauge transformation, then you get a U in front here, okay? Which means that because psi transforms like U here, F must transform like U dagger FU in order for this whole thing to work out nicely, okay? So this transformation must happen from this construction. Okay. So this is the non-abelian gauge field strength. It is the right way to take a derivative of the non-abelian gauge field. And now we can use this to take an action. Okay, construct an action. So let me show you what this action is. The action is the following thing. It's called now the Yang-Mills action. Okay. And it's written in the following way. So it is a functional of the gauge field A. And I'm going to write it in the following manner. It is integral d4x minus 1/4 trace, sorry, 1/2 trace of F mu nu, F mu nu. Okay. Where this F mu nu means F mu nu A times TA. So this is the definition of the Yang-Mills action. So again, this F is a matrix that you get from taking the three Fs and dotting them into this TA. And then you take the product of these Fs and then take the matrix trace over that. It's a 2x2 matrix. Now, this is gauge invariant. Let's check that. If you do a gauge transformation, what happens? Well, from here, we see that this F gets a U, U dagger. This F gets a U, U dagger. This U dagger, U cancels. From the trace, we can move this around and it cancels against this. And so the whole thing is gauge invariant. Okay. There's a question, when and where should one take the trace? You take the trace when writing down the action. The trace is over this matrix, the matrix that is F. F is an SU2 element. So you take the trace over the SU2 matrix elements. It's maybe nice to write this in a slightly more explicit way. Let me just do that for you now. There's a property of the TAs, the Pauli matrices, that if you take two of them and you compute their trace, then that turns out to be a half times delta AB. Okay. So if you plug this in here and then use this to take the trace, then you can write this in the following way, which is maybe a bit nicer. This is equivalent. It's equal to integral d4x minus 1/4 f mu nu a, f mu nu a. Where this a, again, runs over 1, 2, and 3. Okay. So there are three gauge fields, and there's an action here for these three gauge fields. It's f mu nu a times f mu nu a, where f mu nu a is this guy right here. Okay. So the action is completely fixed by the gauge symmetry. Okay, so I realize that there have been a lot of things in the chat. I think most of them, let's see. A lot of it is about renormalization, so I'll answer that at the end. Yeah, okay. Good. Okay, so this is the non-abelian gauge theory action. Okay. Okay, so we are almost out of time. So I'm just going to say one more a quick thing about what this action means, and then I will end the lectures and pass it on to the next person. So you see, in the abelian gauge theory, this F was just d mu a nu minus d nu a mu, which meant that the theory was Gaussian, right? It just had two powers of the A field, and it was fairly simple to understand. Notice that now things are much worse. You see, in the non-abelian gauge theory, this looks like this. We have d mu a nu minus d mu a nu plus g a mu b a nu c f a b c. Okay, and this multiplies the same thing here. So it's like multiplying dA plus AAF. Okay, so this dA is like this guy, and this GAF is like this guy. And so if you expand this out, there are many terms, right? There are some terms that are like dA squared coming from here times here, but there are some terms like dA times AA coming from this times this, and this times this. And then there are terms like AA coming from this thing times this thing. So what does that mean? I did not do this in any great detail when I did path integrals, but basically, if you have only a Gaussian theory, meaning if the field appears only quadratically in the exponent, then you can just do the path integral the way we did it in the last lecture, and you can solve everything. But as you know from the section on the interaction picture, whenever your action has some nonlinearity, meaning it has a cubic term or a quartic term, then you can't solve it anymore. Okay. And then you need to do more work. And so, for example, what this means is that there is an amplitude for one non-abelian gauge field to become two non-abelian gauge fields. This means there's an amplitude for a non-abelian gauge field to scatter into three non-abelian gauge fields, and so on and so forth. And so what this means is that the non-abelian gauge theory is not a free gauge, is not a free theory. Okay. The non-abelian gauge particles interact. So what should we do if we want to solve this non-abelian gauge theory? What we do is we work out Feynman rules and we calculate Feynman diagrams. Okay. So we'll get a non-abelian gauge field propagator, which looks a lot like the one for the abelian gauge theory, except that now it has an extra index, which tells you about the A index, which remember could go from 1 to 3. And it turns out that this propagator now, you can take it to be this in an appropriate gauge. Okay. And then there are also Feynman interaction vertices, which you can calculate, which I'm not going to do, but they're really quite complicated. They're worked out in the notes if you want to see them. But there's a chance basically for 3 of these vertices to give you something proportional to FABC times the momentum. Okay. And there's also some non-zero amplitude for this 4 thing, which gives you something like FABC. So I call this ABCD. There's something that looks something like FABC E times FECD plus all permutations of these things. Okay, and you can work out what these are. And there are powers of G involved here. G, this gauge coupling appears here once, and G, the gauge coupling appears here twice. There's a G squared that appears here. Okay. And so you can work this out. And the remarkable thing is that in nature, this happens. Okay. So as you're going to find in the next lecture in the standard model, there are at least 2 non-abelian gauge theories in nature. Okay. So the standard model can really be thought of as the theory, as the non-abelian gauge theory of SU2 electroweak times SU3 QCD times U1 E&M. Okay. So this part gives us, roughly speaking, the W and the Z bosons. This part involves quarks, and these quarks get bound up together into each other and gives us things like protons and neutrons. And this part, roughly speaking, gives us the photon. Okay. So this is the gauge theory of the standard model, and you'll study the structure of this in much more detail as things go on. The Higgs is underneath this guy. Okay. All right. Let me stop here, and for the last 5 minutes, I'll take questions. Okay.
Should I stop the recording?
Yeah.